Hello, my name's Henry. Um, I'm a physics major at Central Washington University, and a lot of what I do for work, both academically and for fun, is write code. I did some of my undergraduate research on modeling Titan's ionosphere from the Cassini probe. I'll have a link in the description that where I walk through that code there. What I'm doing right here is I want to sort of practice expressing myself, expressing the code I'm working on, expressing the science, and communicating with the outer world and the internet, and doing my best to respond to any questions, comments, or concerns that might come up, and sort of just develop as a communicator of science. What I have here for you guys is a project that I sort of started at the beginning of summer. It took me way longer than I would like to admit, but that's because it was a way of me learning Python. The research that I did with Dr. Snowden at CWU was in MATLAB, which is a whole other coding language. I'll admit I probably should have picked up Python a little bit quicker. Usually, once you get your first code language down, you can snag them all. But I had a few roadblocks with learning what IDE to use, how to use it, importing stuff. Importing was a whole ordeal to me. You don't got to do that in MATLAB. But what my project was here, if you want to learn more about the MATLAB project as well, as I said, there'll be a link in the description where I talk through that code. Really cool stuff. Highly recommend you go check it out. But this project was looking at an object flying through space, passing the Earth, or coming in some sort of close proximity, or even not close proximity to the Earth, and then having the sun as well, where the Earth is going around the sun, which you can see here in green, and the sun is in red, and some object is in blue. Part of the reason I wanted to do this was because I know what to expect, and I know sort of the general idea of how these kinematics work. I know what the force equation is for gravity. I know how fast things can go on a global scale. We have a lot of data regarding the distance the Earth is from the sun and things like that. So I started with importing a whole bunch of stuff. And this video is specifically talking about code and what that code does. If you want another video talking about sort of my reasoning behind making these different leaps, I can totally go more in depth in another video. But it started with declaring a bunch of symbols that I would use in symbolic equations, which would be the gravity equation, the velocity equation, and the position equation. All of these sort of come from kinematics, where g is the gravitational constant, and these are just super common equations. AU is pretty much what I wrote here in the comments. It's the conversion between meters to astronomical units, which are kind of what you see here. This is in meters, like the scale is in meters, but this is 1 AU and this is 2 AU if you ignore this sort of a deal. So a lot of the numbers I got were in AU, and a lot of them were, and some of them were in meters, so I just converted everything to meters. What this massive chunk is looking at the different perihelion and aperhelion distances that the different celestial bodies are, with the sun being at 0, 0, of course. This was because we know that the ellipse or the orbits are elliptical. I wanted to replicate that as well. Granted, it is not that big of a deal. It is not as high tech as I needed it to be, but I also wanted to be able to graph ellipses. I didn't know how to do that, so this was a process of that. So I had the perihelion and aphelions all stored out. I'm only using the Earth right now, but if I wanted to use, say, the radius of Saturn and Jupiter and create something of, I don't know, something like Saturn flying past Jupiter, I have the data for that should I want that. Same here with declaring the masses. This was me sort of thinking ahead and thinking, what if I want to have the sun fly past Earth? Or what if I want to have Uranus fly past Earth with the sun? These also, I could incorporate these in the system as well to see how they would affect gravitationally on my object that is flying by. But at the scale I'm at right now, the Earth was really all that I cared about. The Earth and the sun, because it would fly close to the Earth, so it would have the strongest pull there, and the sun is huge, so it has the strongest pull there. These were sort of just initial conditions I set for my object. I made it positionally. I made it extremely close to the Earth because I know gravity sort of it falls off by the 1/2 or the 1/r² rule. So the farther out you are, the quicker it drops off. So I put it very close so that I would definitely have a pulling effect on it. I also gave it some initial velocity coming towards the sun so that it would hopefully ideally just accelerate. This is the ellipse. This is for the Earth, 365 days around a circle. I make it an ellipse later by applying the aphelion and perihelion distances. These were declaring arrays. I don't know a better way to do this, so what I do is I just declare empty arrays that I then fill in later with appending. And here again is me thinking ahead to myself and setting up a situation where I could, if I wanted to, use Uranus or Saturn or Neptune or whatever. Really, all that I care about here is the Earth. What this is doing is putting that spot at the next spot in time. So by adding the aphelion times the cosine of whatever this angle is, that will get me the x value because the cosine is the x value. And then using the sine, I get the y value. So I am then able to combine the x and the y values into a coordinate grid and plot the ellipse if I wanted to. And I could also find where the Earth is at any spot in time because I'm saving both of these x and y values. Here I am finding the distance between the object and the different celestial bodies. Because I only really care about the sun and the earth in this case, I only worked on those two things. Because this is where the math kind of gets nitty gritty. Same with the acceleration, same with the, the acceleration is again only care about the sun and the earth. Here I am looking at updating the object's position and velocity, and again all of these things I am just declaring the arrays early on so that I can then append to them later. I don't know if this is the most effective version, but it was the one that I found that worked really well for me. Here I'm setting the initial conditions of the object's position, velocity, and whatnot from the values that I declared up here, and that's just to get the array going. In this huge for loop, I am looking at the force of the sun on the object and the force of the earth on the object. That is what I'm doing, what all this math pretty much comes down to. The atan 2 here is finding the angle and then splitting the force into x and y components, much like I had the position in x and y components. By splitting the force into x and y components, I can then apply it to my x position and my y positions of the sun, the object, and the earth. The sun is at 0, 0, but for the sake of making everything look the same, I added x and y components for it as well. So that's what this does here, is the acceleration due to the sun with the sine and cosine, again referring to the angle between the object and the sun. There is a negative value here because the cosine will result in a positive number between 0 and pi over 2. So, and because I know gravity is pulling in, I need that number to be negative. So I put that negative in there. The sine value will also be positive, but that's okay. Moving on, I did the same thing for the Earth, and then I added those things in together in x and y components to find pretty much the general acceleration on the Earth, or on the object. This acceleration is found by F equals ma, force equals mass times acceleration. So that's what all of this math here is, the grav equation divided by the mass of the object, which is the mass I'm looking at. The new object position can then be declared based on the new velocity. We can move it forward in a time step. This for loop will go through the entire time span and move forward each step. So it will take the velocity from before, add the new velocity based on the new acceleration, based on the new position, and then calculate the next position that would be found based on that. And then I simply just plotted it. I set the limits to be 2 AU, just to be, or sorry, -2 to 2, so that we could clearly see what's going on. And again, the Earth is here in green, the sun is in red, and the object is in blue. This was in part me kind of just working through Python, finding a simple project that I could work on that would hopefully not take me very long and allow me to practice my communication. While also a little bit of nervousness. I'm terrified of a massive object coming and smashing into the Earth and killing us all, right? So this sort of put me at ease, whereas I have an object that is starting extremely, extremely close to Earth and not moving all too fast in a celestial scale, and it doesn't hit the Earth. The Earth moves out of the way. Even with the gravity of the Earth pulling, it doesn't pull hard enough that the object would hit the Earth. Part of the reason I did that. I did this project was just out of curiosity of how close can an object get before we're smacked by it. So this was my project. This was sort of just a practice. I can't vouch for the complete accuracy of my modeling. Again, this was something I worked on as a process of learning Python, of teaching myself how to work through Python. I don't know if this appending and declaring open arrays is the best way. So I would love some feedback. Huge thing about this is getting feedback, getting the communication out there. But thank you guys for watching. If you have any comments, questions, or concern, please feel free to drop them. And yeah, thanks for your time. Bye.